Our next speaker, he told me how to pronounce his name, and he said I'd never get it right, so now for sure I can't. Gilad Braca? No? Not even
That's
close?
the preferred corruption. That's what you're supposed to say.
Yes, good. Perfect. Great. Welcome. In his previous life, he was the speaker of the Java language specification, so big deal in the languages space, obviously. And today he's going to talk to us about newspeak, isn't it?
Yeah.
Great.
Thank you. So this is the time for your post-lunch nap, and so Chris carefully arranged so that you would have a suitable sort of accompanying music, as it were. And I'm going to be telling you about 3 domain-specific languages that we have embedded in newspeak in our environment, and that we actually do use as a regular part of the IDE and the tools we build. Before I tell you that, it is a sad commentary on the state of the world that not everybody uses newspeak or even knows what it is or what it looks like. And so I figured it might be actually useful, to tell you just a little bit. I get the feeling that most people here aren't familiar. Basically, newspeak is very much like Smalltalk syntactically and in fact in other ways. And so the syntax is familiar to a handful of you and not familiar to many others. But the syntax, and it's slightly different than Smalltalk. But we'll just go through some basics very quickly. So unary expressions, basically what you need to know is that x space foo means x dot foo parens, right? That's a method call on x is the receiver, foo is the name of the method, and the red stuff is the stuff you don't need, because it doesn't convey any information whatsoever. It conveys information in the languages you're used to, but it doesn't convey any information in newspeak. The point of the dot in all these languages is it's an operator. It's the object member selection operator. And you need this operator to distinguish it from all the other gazillion operators your typical language has. The only operation in newspeak is virtual method invocation. And so we know that already. So there's no need to say that. Likewise, we have this novel idea that if there are no arguments, you don't have to write them. There are no arguments. And we can do this, again, because we don't have to distinguish this from a variable or a field or anything, right? So we don't need an empty list to tell us that there are no arguments. We can see that there aren't any. The other, and this is good for DSLs because, they usually don't need this extra noise. Binary expressions, they mostly look like what you'd expect. So this evaluates to 12. And that tells you that the unary ones, like 3 factorial, bind tighter than the binary ones. And if you were doing this in whatever stuff you're used to, you might write something like that. You probably can't exactly write this. The point is that plus is just the name of a regular method. Virtual method, overridden, it's just a different string that you can use for a method name. It's not an overloaded operator or any of that rubbish. Okay? It's simply a method. So you can write that, and if you can't write that, maybe you can write this, and you probably can't write that because it'll think it's a floating point number, but this is, you get what it means. Keyword expressions. So Windows version :7 plus 0i, right? The fact that I'm using an imaginary number as the Windows version is just a coincidence. It's not intentional, right? So again, it means this, right? And again, that tells you that binary expressions bind tighter than the keyword expressions, and all these versions show you, again, the precedence. And if you need more than one argument, then you could write something like this, add :1 to COBOL, which would mean this. And that'll evaluate to COBOL 2.0, otherwise known as Java. But the real advantage of this notation that you're not used to and you can't be bothered to learn, et cetera, is that in a dynamically typed language, you can't get arity errors. You cannot pass the wrong number of arguments and let JavaScript go down some rat hole. It just cannot happen. The syntax prevents that. You don't need a type checker to do these sort of things. So that's really the technical property. It also reads rather nicely for all these sort of data-oriented things, of which we've seen several, and we'll see some here as well. So the other thing is, when I made this talk and I saw the timing, I saw that I had an hour slot, and I said, yay. And sometime much later, Chris mentioned that actually it's 45 minutes. So we may not actually get through everything. So new shell is a class we have in our environment that's designed to let you run shell commands from within the language. So this doesn't read exactly like a Unix script. You don't need to know what the semantics of classes are and all the fun stuff about newspeak. Basically, this is newspeak code, right? It's an internal DSL. It doesn't look exactly like shell commands, but it's pretty close. And it basically works with does not understand, right? So the new shell takes the trouble of trapping whatever method that you invoke on it and going off and looking something up in the shell and starting up a process and running it. So in the interests of, how does this work? In the interest of actually showing you that some of this is actually real, we've got here an inspector on an instance of new shell. And we should be able to actually get it to do something. So there's a string here. When it prints the string here, it doesn't seem to handle, you know, it doesn't actually split the new lines out. So you're getting them concatenated. But this is what's in the current directory. And if you evaluate this guy, we get more detail. And they all work. And the nice thing, again, because you have the access to these shell commands embedded in your language, is that you can combine them with things like closures and all the general features that your language have and your typical shell command language sort of isn't really great at, and do things that are a little more interesting. So we can get an ordered collection here. So every time you evaluate this, it gives us a link to a page that will let us basically open an inspector on the object that resulted. So this is an ordered collection of the strings that represented the individual file names. So just to point out that it actually is there, I would like to get some time and do more work on it to make it a bit more general. It doesn't do pipes yet and things like that very nicely. But there are different ways of doing it. The basic principle is we go off and ask, use does not understand to do it. So it's one of those standard tricks you can do in dynamic languages. And the reason you have to put value there, we could just have ls go off and print the directory. The problem is that every command has a different number of arguments and they vary and so forth. So what we actually get is an object back that can get its arguments later, right? So that adds a little overhead. And there's different ways of encoding this. So minus, because there's so many commands with a minus operator in the shell, we added a method minus to this thing that already evaluates that. So that's kind of a very cheap little trick that makes it much easier to communicate with the environment. And that's particularly important in the tradition we're coming from, because Smalltalk usually does not deign to communicate with the environment because the environment is ugly and messy and not really fit for Smalltalkers to actually touch. Ew. But we actually realize that's a problem, and so we've endeavored to make newspeak a lot friendlier for interacting with the nasty world that's out there. Probably most of my time here will be spent talking about a DSL for parsing, and maybe we'll get to the UI part. So parsing. Parser Combinators. I'm guessing not too many people here really know what Parser Combinators are. No massive disagreement. Yes, Guillaume. Okay, so I didn't say everybody, but I guess most of you don't know. You probably know. But so here's some piece of BNF. It's standard identifier, right? This is what it looks like in newspeak. Doesn't look quite as nice, but it's pretty damn close, and it has the advantage that it actually runs. So you can actually parse something with it. And this is actually what these are calls to a library, and in Javanese it would look something like this. So we'll go through and explain what all this means, but basically it's an approach that comes from functional programming that is a very elegant approach to parsing. And one of the things I'm going to disagree with what was said earlier is I don't see any conflict or contradiction or anything between object orientation and functional programming, and you can have it all and combine them in one go. So it can be combinator-based and compositional and dynamic, and this example will actually show some of this stuff. So how does this actually work? What this thing is basically what you'd think of as a field definition. Right? There's a when we define a grammar, we basically define a class that's a subclass of some particular of the Parser Combinator library, and for each production we're going to define a slot. a field, instance variable, whatever you want to call it. This one is named ID, and the equal sign here is a definitional equality. It means that this is a read-only slot that will be initialized to the expression on the right-hand side. So how do you read this thing? Basically, this is a method call, right? The method in question here is comma. That's a method name, and it represents the sequencing combinator. What will you do when you evaluate a method? Well, you have to figure out who the receiver is, for starters. And letter, again, is a method call. We will have defined this somewhere else, and I'm not showing it to you right now. But this method call will give us an object. This object was going to be a parser that knows how to parse one letter. Any letter but one. That's the receiver of the call. Now we need to figure out what the argument is. Well, that's a method call too. It's an invocation of the method star. You can imagine a dot there after the parentheses, right? So the receiver again, which is again one of those binary expressions, its receiver is letter. So we get another one of these letter parsers. Then we evaluate its argument. We get a parser that will parse a single digit. Not a very complicated thing, but the whole idea here is to build big things out of small blocks in a very uniform way. Now we can finally evaluate that method call, and that'll give us an object that is an instance of an alternating parser. This is an object that has two subparsers. And what it does when it's asked to parse something, it asks the first parser to parse it. And if it finishes, it's happy. And if it fails, it asks the other one, and only if both of them it fails, it gives up. So this isn't quite BNF. This is what's known as PEGs, parser expression grammars. This is a serious formalism. There's Popple papers, the whole thing backing this up. I didn't know this when I wrote the library, but it was gratifying to find out that I was on a solid foundation anyway. Yeah, exactly, and I do too. So basically, the nice thing about this formalism is there's no ambiguity, right? You are giving priority explicitly to the left. And that means you never have ambiguous grammars, you never have shift, reduce, all this. LR parsers should be dead and buried and exiled to the ends of the earth. Okay? And so a lot of the complications that brings, you don't have to deal with. So once we've got this object, we can invoke star on it. That'll give us a parser. You can guess what this does, right? It has a subparser, and it calls it in a loop. And it collects the results in a collection, which is what it will return. And should the subparser fail, it doesn't fail, it just stops. So in particular, if the subparser fails the first time, you get an empty collection. So it's 0 or more repetitions, which is what you would expect star to do. And the next phase, we finally invoke the sequencing combinator. It has two subparsers. It asks the first one to parse, then it asks the second one to parse. If either of them fails, it fails. And now we have this tree of parsers, which basically is an object that will parse first a letter, then 0 or more occurrences of either a letter or a digit, which is exactly what we wrote down. So we're encoding an abstract syntax tree of BNF into an object graph that we can actually interpret and execute. So it's dead simple, really. Now, I do want to take a minute and argue why this actually looks nice.
What's that period at the end of star?
The period, think semicolon. Okay, it's a statement separator. We'll actually get to that in a moment. So everything's relative. If it's pretty, it's because something else is ugly. And why is it really ugly? If you compare it, so this is the prettiest of all. This is BNF. It was designed, purpose-built for this. The whole world uses it. It has nothing extraneous. This, on the other hand, is awash with extraneous stuff. Everything in red is completely useless. It is solution space cruft. It is stuff that you are forced to deal with because you chose to implement the solution in a system that needs this information for purposes that have nothing to do with your problem. They come from the solution domain, not from the problem domain. So all the red stuff is pure noise. BNF has no noise. We have the dot. Yeah, we also have the dot, just like the semicolon here. So we have a statement separator. But that's about it. The purple prose is just things that actually have to do with your problem, but they're sort of suboptimal, right? You'd like to express them in a more concise form, and You know, this is also purple, right? Because we don't have postfix operators. But overall, we're not doing too bad. And it's always good to quote someone, you know, to back you up. So Alan Perlis has an infinite supply of great quotes on programming languages. And this one is really key to the whole domain-specific language story, right? Programming language is low level when its programs require attention to the irrelevant. And when you try to encode this sort of stuff in a general-purpose language, generally speaking, there's lots of irrelevant stuff you have to deal with. BNF is a notation designed to deal with grammars, and it doesn't have irrelevant stuff in it. So it raises the level of abstraction. That's really the key goal of domain-specific languages in my mind. So I just wanted to bring this up. And now let's try and see how this actually works in practice. So you would define a class, subclass of executable grammar that comes from the framework. And basically, you've got a set of productions. What this shows you, among other things, is that unlike, say, the M-grammar stuff, we're not separating the handling of lexical stuff and syntactic stuff. This is scannerless parsing. So everything works on the same basis. So a digit is a character between 0 and 9, which you knew that, I think. And a letter is a character between lowercase a and lowercase z, or a character between uppercase A and uppercase Z. And ID we've talked about. Now this is interesting, right? What is this doing? We've been basically parsing character streams and gathering up collections of characters. It would be nice to tokenize, but we're not doing anything special with a tokenizer. We're not introducing a lexer or anything explicitly, right? So at some point, we have this parser ID that parses a stream of characters. But we really want to skip white space. We want all the things that a lexer will do for us at some level. So token 4 is a combinator. It's a method in the framework. It takes a parser and gives you a new parser that pretty much parses the same thing, except it'll skip white space and wrap it in a token object and tell you in which indices in the input stream, you know, from where to where, the kind of information that you need. And we do this for lexical things like this. We can do this directly from a character for the hat, which we're tokenizing with the production below. And we have one expression in our language, which is identifier, because otherwise it won't fit on a slide. And it's important for your language to fit on a slide if possible. Brad, yeah?
What are your banana clip looking thingies here?
OK, so this is syntax for essentially classes, right? Think curly braces. At some point, I'll get around to changing it to curly braces so that I can take over the world. In the meantime, in the meantime, it's just essentially the newspeak class has basically an initializer segment and a body and stuff. And I'm not going to get into that in this talk because it's not terribly material to what I'm presenting. So anyway, returns, these are small talk-like return statements. They have a hat and then an expression. So it's a hat followed by an expression, right? Fairly easy to see. And in the interest of, again, proving that it actually exists, we'll go and find it somewhere. That would probably be this guy. I don't know if you can see it, but this is basically that same grammar. This one's too long, so it's been shortened, so we'll open it up. And I think I have, oh no, it doesn't work on the second screen. This is zoom it stuff. I'm sorry, I'm not a Windows person. I don't know how to zoom on this machine. So anyway, you just need better eyesight because of that. But trust me and the people in the front row, this is exactly what the slide said. OK? So where did our slides go? Slides went somewhere. And there's several points I'd like to make about this mechanism. First of all, you notice there were no semantic actions. It's just the grammar. So where do the semantic actions come in? So that's what this slide is about. Basically, this is the production we had before. This thing that says wrapper colon, that combinator basically takes a parser and a closure. The stuff between the square brackets here, that's a closure. What it does is it parses the same language as its receiver. But the result it returns you is different. It uses the closure to process those results and produce a new result. In this case, it's building an AST. Right? So in terms of the sort of tree diagrams we had before, we've got this tree of parsers with the sequencing, and we've got another node, a wrapping parser around it, that will do that wrapping with a closure for us. And the nice thing is if you can do that, then you can separate your grammar from your semantic actions very neatly. Now it's just formatted, but once I did that, I realized I can separate them completely. I can put the grammar in one class and put all the semantic actions in a different class. So what we're doing here is we have one class which defines these slots, which are always in newspeak access. Everything in newspeak is a method call, so you never actually access slots directly, which means you can override slots with methods. And so we have a method here in the subclass. It calls the super, gets you the parser that was just recognizing things, invokes the wrapping combinator on that to make it produce the AST. Now you do this for all your productions. Since they're all self-referential, you basically have a parser that actually is producing ASTs or whatever it is you need to do. And that's very handy. The ability to separate this is something you generally don't see. Most of the time you find people cluttering up their grammar with some sort of semantic action. There's lots and lots of reasons why you don't want to do that. Other things, obviously, you can do. So this is actually this is the example of doing that for all the productions in our language. So we do it with identifiers. We wrap them in variables. We do the same thing with the return statement. Another thing we can do, right? We can extend the grammar. We can extend our language by adding. In this case, we add some sort of if statement. Now, this is an important point about internal DSLs, right? We don't have to invent an inheritance scheme for our DSL. Our language already has one, and we inherit inheritance from it. Whereas if we did an external DSL, we'd have to replicate all the abstraction mechanisms that our general purpose language needs in order to get that same kind of functionality. So we can subclass grammars without having done anything special. That just falls out. Now, if you look carefully, which I'm sure you didn't, and I'm glad, because otherwise someone would interrupt my flow with a question when I'm not ready for it, so it's good you're not looking too carefully. But if you see, there's a loop in this grammar, right? There's mutual recursion going on. So if statement refers to statement, which refers to this guy, which refers back to if statement. And that's very common in grammars, right? Mutual recursion happens all the time. Now, if we run this, right, initially we have an object, an instance of one of these grammars, and it has all these slots, and initially they're nil. And what happens is the initializer that gets executed is going to evaluate all these expressions. It's basically going to take our grammar and build these trees into that instance. And it'll turn them into parsers. As it goes along, it happens in order. And at some point, it'll get to if statement, and bad things might happen, right? Because if statement is going to try to call statement, and statement hasn't been initialized yet, and there's no parser there, and nil doesn't understand parser combinator operations, and gee, the whole thing doesn't appear to work. So there's different ways of dealing with this, right? So Haskell, that's the ultimate solution, right? They do not stoop to worry about ordering among things, right? That is beneath them. It's lazy. Everything shall be done when it needs to be done. You will never know when it needs to be done. If you try to debug it, you'll never figure out, but it'll perturb it. It's all quantum mechanical. But it is great for hosting a domain-specific language, because in languages we always very often have forward reference, and you never have to worry about it. Now, parser combinator libraries are actually pretty much originate in the Haskell culture, and it's not surprising because they can handle it very well. When you try to do it in ML, you start wrapping stuff in lambdas, right? So you have to delay the evaluation of these arguments typically. And I had a library originally in Smalltalk that worked this way, and I had to wrap the arguments in these guys, which are closures, right? Fortunately, Smalltalk has a lighter weight syntax for lambdas than the functional guys do. But still, it's still essentially, right? It's blood. It's cruft. And that's not nice, and that's not what I showed you, right? So obviously, I wouldn't tell you this unless I had a better idea. So let's reflect on this business of being lazy, right? What do you do in a compiler? In a compiler, when you encounter this situation, you set up forward references. So why don't we do that? we basically have, the way things work is the initializer of objects of a subclass calls the initializer of the superclass, which gives us the perfect hook for our framework to come in and intervene. So what it does is it's going to initialize all the slots reflectively before the initializer of the class actually executes and stick in these forward reference parsers, which will understand the parser combinator operators and won't blow up. They have no idea what they're going to parse right now, but things will work out. So I can then go happily, replace them when the actual initializer occurs, fill them up with parsers, and nothing bad happened, and I didn't need to wrap things with closures. Now, of course, I've broken the loop. That's why nothing bad happened. But I needed the loop, right? There was a reason for this loop. So I'm going to have to fix it. So what will happen later is that these forward reference parsers will complete the loop. They actually complete the loop lazily. The first time you ask them to parse something, when they were constructed, when you reflectively initialize slot X with a forward referencing parser, you told it what the name of the slot it was serving was. And it can use that information to go look now and see what's really in that slot. That's the parser I need to forward to. And from then on, it'll just forward everything to that, and parsing will proceed exactly the way you want it to. And you, the poor guy who writes the grammar, don't have to worry about this. So essentially, we've completed the loop, and this is the moral of the story. Basically, you can emulate laziness with reflection, but not the other way around. Reflection is a very fundamental thing. Yeah.
What's the hook that you use, the pre-initialization hook? Is that something that's built into newspeak?
Okay, so the way this works, you subclass executable grammar.
Okay.
The initializers, instance initializers get called in the traditional order, right? So the superclass initializer happens first. So that's essentially my hook. That means that executable grammar looks and sees what object am I, what slots do I have. I'm going to slam in these forward reference parsers. Even if I have some service slot, some state that I decide to do in some place, it doesn't matter. It'll be overwritten later. But if it is a parser, there'll be a forward reference parser there. So it's just one of those cheap tricks, but it's kind of neat. And yeah, Phil isn't here. Otherwise, I'd get in trouble saying this. But anyway, that's how we avoid the need to wrap everything in lambdas, and we can therefore get this thing written in a very natural notation. And this sort of thing can occur in pretty much any situation where you have forward references. You might want to do something like this. Now here's another problem, right? So I had one grammar, and I showed you how to extend it with a parser and a subclass. And I've shown you how to extend the grammar with new productions. But now I need a parser that actually parses this extended grammar. And I've got this classical multiple inheritance problem. If I subclass this grammar, then all the stuff that knew how to parse all the other productions is gone, right? Unless I have multiple inheritance. And it doesn't help me to do it the other way. And I certainly don't want to do it both ways. So the answer, of course, is mix-ins. Right? So we want to mix in. You can do this in a couple of different ways. But let's say we took the grammar class, mixed in the parsing functionality from the first parser, and then in the subclass, all we have to do is add the stuff that parses these new productions. Right? Again, internal DSLs work well for this, because if I did my external DSLs, I'd have to invent a mix-in scheme for my DSL. And that can be tricky, and the odds are that you won't get it right. And in any case, it's a lot of trouble. But if your general purpose language should be able to do mix-ins. Of course, it doesn't. Not yours, but a good one. So it'll look something like this, right? So we define this new parser, and its superclass is basically that notation over here. My laser pointer is broken, so up there. The weird thing is a mix-in application operator. And so we extract the mix-in from the example parser1 class and apply it to the superclass of the complete grammar. And that will serve as a superclass for this whole thing. Then the only thing I need is to fill in the method for building the if statement AST. Right? So again, it's kind of interesting that we get a lot of leverage out of using an internal DSL. I guess I should, yeah, I meant to show you these things, didn't I? Let's see. So who would this be? Oh, I think we'd see it here. So this is example parser 2. It has the if statement method here with whatever it's doing to create an if statement AST. Its superclass here is actually super parser, which is defined up here to be example parser1 mixin using the mixin application operator. And that's because the implementation actually right now, and for the past 2 years I haven't gotten around to fixing it, doesn't allow you to actually put this in line here. But this is no big deal. It's such a no big deal that I haven't bothered to fix it. But sometime I'll get around to it. But basically, again, this is the exact example that you saw in the slide. So what else can we say? The point here is the thing that actually really distinguishes this from parser combinator libraries in the functional world, one of the key things that distinguishes it is this ability to factor out the grammar from the semantic actions. And that's really useful. If you want to you know, take this grammar and implement it on different backends, different systems that you may be mapping to their ASTs, to their framework, but they each have a different one, you can share the grammar. If you're doing it in one environment like we are, there are many things in an IDE that could use the grammar, and not all of them want the AST. The syntax coloring doesn't want the AST because we want to colorize comments and things like that. And so it's nice that this whole framework also works on the lexical level, and we basically have a different subclass of the grammar that knows how to do the colorization. And we actually use this stuff. I'm not aware of a lot of environments. Actually, I'm not aware of any environment. So someone told me that GHC or somebody in the Haskell world actually did use combinators in their actual system. Because the typical thing, you ask the functional guys, well, are you using parser combinators? I mean, you've been publishing these lovely papers for 20 years. Does your compiler use them? Oh, no. Oh, for real? You mean, no. This is for our students. We publish, right? They don't actually use it because they have a reputation of being slow, and ours are as slow as anybody else's. But we can get away with this and actually use it in our IDE, and the code you saw actually runs through a library like this. And the colorization, every keystroke, when you type in this thing, it goes through parser combinators. We get away with this even though we're running on a squeak interpreter, for God's sake, because of the nature of the interactive environment, which basically is all little methods that you're incrementally adding, right? So we never have huge piles of code that we have to wait for. Occasionally, you can file in something from disk, and the parsing, it would be nice if the parsing was faster. And in fact, there's a master's student out in Germany now who I hope will fix this. But it can be made fast, because the other point to remember is we have all the information. We have a grammar. If your grammar happens to be an LR grammar, we should be able to compile it. We should be able to do everything that Yak does without exposing you to the horrors of that system. Right? We should be able, there are several ways to do this. One way would be to do drag and book style transformations on that tree that we've produced. Other ways would be to do it dynamically, sort of jitting, as it were. So the information is there in principle, and it is a small matter of programming to actually make these things run fast. But they should, and I hope we'll get there, and I hope we bury Yak and Lex where they belong. So that was parsing.
Quick question.
Yeah.
Do you think it's possible to define newspeak's grammar in newspeak? Like
It is defined in this.
It is. So
Yeah.
it's all
Yeah. These. Hang on a second. We'll find it. So let me find it for you. Well, the truth is, of course, we've got two compilers. The old one in Smalltalk that actually is what's running here. So there's a Smalltalk library that still uses the closures. That was what I alluded to earlier. And the new compiler that actually works but isn't actually hooked up here. So we'll find one or the other. You speak to compilation. No, that's actually not the one I want, but it'll get me there. So this is the compiler, but from there I'll find where the parsing is. This looks plausible, doesn't it? You speak to grammar. And inside it is a nested class. And this is the whole story. So let's find the production that looks nice. I could tell you why it's colorizing it red right now, but you don't really care. So an access modifier is either a tokenized symbol. Symbol is an intern string, either private, public, or protected. And there's something nasty why that white space is there. But basically, these are the productions that are actually used. So yeah, you can do, because pegs are a very general framework, right? Pegs can do pretty much anything. I mean, they can't do every context-free grammar. In fact, no one knows exactly what they can do because the comparison between them and those is still an open theoretical question. But it's very, very broad. The other point is we could actually make it broader, right? Because we're just a library, we could add a combinator that did the real BNF thing and allowed us to define ambiguous grammars. It would PEGs backtrack already. This one would backtrack a bit more. But in practice, it's very rare that you want the actual BNF. You want the PEG. You usually want to prioritize them, and you arrange your productions with the sort of longest match first. And that works out very, very simply. Another thing that's different from the functional approach, since we aren't functional, we can do context-sensitive grammars if we want to. We can define subclasses that have state, and there's all kinds of tricks you can do. So it's kind of a fairly nice framework. Okay, well, let's see what we can do with our third example, which is the UI. So these browsers I've shown you, they're all running on a framework called Hopscotch. That's a high-level GUI application framework. And it's sort of a document-based level framework. It's not a widget-level framework. There's a widget-level library below it. And so it's document-based. In a way, it's kind of like a little like HTML or something, but it's kind of nice and clean. It manages navigation for you. So these browsers, this is something the framework does, not the IDE per se, but the underlying framework manages all this ability to go back and follow hyperlinks in the IDE and all that kind of stuff. It pretty much ensures that you do not produce modal interfaces, again, because of the navigation paradigm. You can be in the middle of something, leave it there, and travel around your browser through hyperlinks. And the reason I'm talking about it here is that it provides you with a DSL for composing pieces of graphical presentation out of more simple elements called fragments. And so it's a fragment. That part is basically a fragment combinator library. So this theme of combinators, of taking basic pieces and having an algebra on them that grows bigger pieces from them, is very big in the functional world, but there's no contradiction. I mean, you can do this in an object-oriented style, and it's actually a very natural match, because your fragments tend to have these combinator operations as methods on them. And so you compose these things. You start with some basic things that provide you atomic fragments, and you can do compound ones using various combinators. So typical combinators, a blank space in somewhere would be a very low-level atomic one, or a filler is actually an elastic space that'll fill up, any kind of stretch and fill up things. If you need a button, there's something that'll give you a piece of presentation that implements that button. You'll pass it a closure as an argument for what it actually does. If you need a hyperlink, it's very similar. Image, a menu, there's all kinds of things that do your basic pieces. And then you compose them out of rows and columns, and you can center them, or make them collapsible. Or if you have a piece of UI that you need to do in the background because it's expensive to compute, there's a deferred combinator, takes a closure that computes a fragment and goes off and does it, and will fill in the UI at that point when it's done. We do drag and drop this way as well. So there's essentially a draggable combinator that lets you make something be draggable. And I should be able to show you, again, some of this stuff. Though we're okay. I'm not sure if I can do the whole demo, but I can certainly show you some of this stuff. So this class, you don't really care about that. Let's show you basically what something looks like first, because I'm afraid I'll run out of time, and we can demo more if we get a chance. So here is a method. Let's get rid of this colorization for a minute. Do I have space? No, that's not this. That was the grammars. No, maybe I don't have it, or maybe it's. What, this guy? Yeah, this guy. That's what we wanted. Of course, with two screens, it pops up in the wrong place. But this is that application class that I showed you. It had a very simple definition. It's basically a file browser, and the demo will let me switch through and make those definitions more elaborate. but it basically shows me, you know, a view of a given directory. That's what I evaluated in this workspace here. So if I go back to File Presenter, which is the thing that manages this, here's one of the methods it uses. It hasn't been used in what I showed you yet, but it did serve to tell the ID enough so it knows that these things are valid. Right? This is a user-defined combinator, right? It's just a method. It takes a fragment as an argument, and it builds a column that's gray, and the column has some vertical padding, 2 blanks on each side, and in the middle it'll put a row, and that has horizontal padding. In the middle it'll put an elastic space with whatever fragment I send it, and that will produce a bar, a gray bar with whatever thing I want to display inside this gray bar. And in some cases it might be something like the name of the file I'm looking at. Now right now I've got this at the beginning of the demo, which I don't believe I'll have time to go through, but the initial stage of this is defined in a thing called file presentation. This is a very basic combinator. It's called label : you send it a string, it gives you a piece of presentation that'll show you that string, and we use it to display the file name. Now if I try and make this more fancy by going to, say, something like definition 3, just to shortcut the whole thing, then let's see if I can refresh this. Yes, so now it's more interesting, right? I've got a hyperlink here, and it's expandable. So now you can look at my directory, and we can go through it and look at subdirectories like newspeak and so forth. And this is all using the same kind of library that I was doing before. And these gray guys, right, this is the result of that bar method, right? It's just taken those labels, which are fragments, which are now not labels, which are now hyperlinks. They're the link combinator, and embedded them in this little piece of gray stuff. So it's a lot like the things you write in XAML or JavaFX or whatever, right? You have these domain-specific notations that they glue stuff. They have columns, they have widgets, whatever. But we didn't have to do anything special, well, except for code the framework, which Vasily did. But we didn't have to change our language very much because, again, the much maligned classic Smalltalk syntax is very natural for these kind of things. You know, name, colon, some structure. We have literal tuples in there so we can aggregate them. And unlike Smalltalk, we don't have to make the receiver explicit, so we get rid of one last bit of cruft that actually shows up in Smalltalk code. And you get something that looks as if it was a purpose-built notation for a lot of these data-oriented things, like some of those trading examples we've seen over the past 2 days. A lot of data-oriented domain-specific languages, they just happen. Of course, they're not just data, right? You can put in abstractions, you can call methods, you can define new abstractions, etc., which is both a pro and a con, right? Because there's people who think that the biggest deal about a DSL is that it should constrain the input. Yeah, there's too many people in computer science whose interest is to constrain everybody. Okay? Lest they ever make a mistake, lest they ever do anything, in fact, because usually that one thing leads to another, and pretty much you're perfectly safe as long as you don't breathe, because the air, who knows what's in it. But you know, I prefer the dynamic approach, even though I've spent far too much of my career doing type systems, and type systems can be useful. They're useful mainly as documentation, right? It would be nice, for example, to write here that this actually took a fragment and returned a fragment, right? And apparently it likes it. And, oops, wrong. This is the Apple button. Sorry, I'm not used to. We need control here. So we actually do have a notation for optional types, but unfortunately they don't mean much right now. Because doing a real type checker for this stuff is really hard because it is so frigging dynamic. But in any case, their main value is as metadata for the types. But that's sort of a tangent. So yeah, we're actually 2 minutes ahead of schedule, but basically this is the essence of what, and let me see if I have any more wise things or any things to say in the slides. But yeah, well, I'm not going to show you this, but I'll mention it because, again, it's one of those tricks that you use in dynamic languages, right? It goes back to at least a Newton script. When you have these visual presentations, it is very useful to refer to the visual thing enclosing you. And Newton script in particular had this wired into the language to let you call up the visual hierarchy. And we don't have this in the language, but we have a library operator that let you send up a message to your surrounding widget. And we do that with does not understand, of course. So that's another, again, the same tricks. They come up over again. But as you can see, the functional stuff and the dynamic stuff, they don't have to, you can use both, and they complement each other. And Chris is here, looming, and I have 9 seconds according to my watch, but I'll stop now just to be safe.
So my question was, the newspeak actually looks really cool to me.
Use a microphone.
No, I'm good. Thank you.
It's his conference.
You can hear me? Yeah.
You do whatever you want.
So, can I get this somewhere? Can I download it? Can I play with it? Can I use it?
Let's skip the related work. This isn't an academic conference, so I can ignore all the stuff that we're stealing.
Pretend you invented it.
I invented it all. Mwah. Yeah, well, I did want to mention the conclusions, but we'll skip those. Basically, there are conclusions. The small talk like syntax works great. Dynamic typing and reflection does not understand. All that stuff is really good. Mix-ins, blah, blah, blah. Here, this is the answer to your question. So it's open sourced. Those of you who are at lang.net in January of last year may remember that I made a fairly blatant pitch. If someone that would express an interest that would help me convince my management to open source it, someone did. And that was very helpful. And now that I don't work for them, I can even say that. But basically, we did get it out into the free world. And you can download it at that thing. And it's a prototype, right? But definitely early adopters, you should be able to do a lot of stuff with it. Supposed to be, what is supposed to be there?
newpeak-language.org.
Well, you see, that's what happens with these dynamically typed things, text, right? If only we had somebody who would check every. Okay, so thank you. I think I can fix that. So yes, it is the domain is right. It's newspeak-language.org.
So my next question is, who's using it in the world?
Okay, so me, isn't that good enough? There's a sad story here, which was that the whole thing was funded in the context of an incubation at Cadence. And for whatever reason, you know, the way the finances have gone, Cadence canceled the incubation. Well, it canceled all its incubations. It shut down its research lab. It did a lot of things that were very forward-looking. But yeah, they had money problems. This happens to the best of us. And so we were embedded in that incubation, and we got essentially canned as part of that. We weren't explicitly canned because they didn't know we existed. Had they known, we would have been canned much earlier, obviously. But in any case, there was a product that was actually given to early access customers that was developed using this, and they actually were willing to pay big bucks for it. But you know, the way, you know, you've all seen this scenario many times. We weren't finished, and we weren't producing enough revenue to cover our expenses, and so we're dead. And so essentially now there's some, you know, open source volunteers and you know, people who like that stuff who are playing with it. But no one, there's actually a group at Cadence that is interested in using it still, but they have to convince their management. You don't want to know. So nobody. But it's a prototype, and it's cool, and feel free to download it.
Thank you very much.